On Friday, we analyzed elastic and inelastic collisions. We learned what the difference between an elastic and an inelastic collision is. There's lots of ways to classify collisions, right? One-dimensional, two-dimensional. That's one good way of classifying collisions. Explosions, collisions. That's one way, one good way of classifying conservation momentum problems. But another way of classifying collisions, only collisions, not explosions, is whether it's elastic or inelastic. Now, an elastic collision differs from an inelastic collision, not in the momentum sense. Momentum is conserved in both of them. It doesn't matter whether you've got an elastic or inelastic collision. As long as you have an isolated system, momentum is always conserved, always, as long as you have an isolated system. But kinetic energy isn't. If you have an elastic collision, kinetic energy is conserved. Kinetic energy doesn't decrease. But if you have an inelastic collision, kinetic energy does decrease. So, the general rule of thumb here is this. You want to find out whether it's elastic or inelastic, calculate the initial kinetic energy. Calculate separately from that the final kinetic energy, and then compare the two. If to the right number of significant figures, those values are the same, it is elastic. If to the right number of sig figs, those kinetic energies are different, then it's inelastic. Does that make sense? There is a shortcut that we can take sometimes, but not always. What if we have two objects that are coming towards each other, they collide with each other, and they stick together? Do we know without a calculation what type of collision that is? Right? Yes, good. We know for sure if they stick together, it is inelastic. There will be kinetic energy loss every single time. Now, if two objects come together and then they bounce apart when they collide with each other, do we know what kind of collision it is there? If they stick together, it's inelastic. If they bounce apart, it must be elastic, right? No, it could be it could be elastic, but it could be inelastic as well. In all likelihood, to be honest, even if it bounces apart, it's still going to be inelastic in all likelihood. We don't know for sure until we crunch our numbers. Okay, the only one we know for sure is if they stick together, without doing numbers, that is. But, excuse me, since most collisions are inelastic, the vast majority of collisions are inelastic, even if they bounce apart, they're probably going to be inelastic. Now, what kind of collision? Give me an example of a collision where they bounce apart, where it's probably going to be elastic or close to elastic. Okay, two argon atoms or two subatomic particles. If you've got subatomic particles colliding, that's not going to be almost elastic. That's going to be truly elastic. The reason because they can't compress any further, right? They can't get any smaller. You don't have that conversion of kinetic to elastic potential energy and then back to kinetic energy. So therefore, you don't have an energy loss. Two pool balls, similar type thing, right? Although it's not perfectly elastic, it's going to be very close to elastic because the pool balls don't compress. Two curling rocks, same kind of deal. They don't compress very much, so you're not going to lose very much energy. Hey, if you do lose energy, if you do lose kinetic energy, usually what form is that energy going to take? It's converted to what? It's not destroyed, right? It's converted to what kind of energy, usually, right? Usually heat, right? There could be some sound energy. There probably will be some sound energy, right? Two pool balls hit each other, there's sound energy. But although it might not seem like this, there's actually more heat generated than there is sound energy generated in that case. So if we lose kinetic energy, it's inelastic, and most of that kinetic energy that's lost will be lost in the form of heat. All right, we got two questions here that we had for homework on page 482. Let's take a quick look at one or both of those. And then we'll take a look at the assignment that we had do yesterday, and then we're going to get back in just a second here. All right. Either of these that we need to go over here, guys? We're going to go over one no matter what. If you don't have a preference, then I'll just pick one. But yeah, we can. Yeah. Question number one says, a 45-gram golf ball is stationary on a green when a 185-gram golf club face traveling in horizontally at 1.24 strikes it. After impact, the club face continues moving at 0.760 meters per second, while the ball moves at 1.94. Is the collision elastic? My guess on this would be what? Let's cover up the answers. Okay, you've probably already seen the answers there, but what do you want to guess on this? The golf club hits the golf ball. Do you think it's going to be elastic? Do you think it's going to be inelastic? Yep. Okay. Okay. Why would you assume it would be close to elastic? Okay. So the golf ball can compress a bit, but it's not going to compress very much. The golf ball actually doesn't compress a whole lot when you hit it with a putter, right? But golf balls are actually, in the end, quite compressible. If you hit it with a driver, the golf ball actually compresses to a size that is barely twice the size, sorry, barely half the size of its original size. So if you could see a golf ball, if you could see fast enough, if your eyes were and your brain were quick enough to pick this up, when a golf club, a driver hits a golf ball, you could actually see the golf ball becoming only slightly more than half the size of its original size. So golf balls are pretty highly compressible, which leads me to think that this is going to be probably an inelastic collision. Even though it's only a putter hitting it, I'm thinking this is still going to be inelastic. Okay, let's check though. Let's calculate EKI. We're going to say 1/2 m1 v1 I squared plus 1/2 m2 v2 I squared. If those masses were the same, could I cancel them? No, we couldn't. Because they don't appear in every term. It doesn't appear in that term. We have to use grams here because the units don't cancel out either. The golf ball is, that was at rest, wasn't it? So we're going to say the kinetic energy of the golf ball before the collision is 0. The kinetic energy of the club before the collision is 1.24 meters per second. Who's got a value for the kinetic energy there of the golf club? 0.6535. We're going to round that to 3 digits here. So we're going to say 0.654 joules. Kinetic energy before the collision, 0.654 joules. Okay, let's find the kinetic energy after the collision. We're going to say that's 1/2 m1 v1 f squared plus 1/2 m2 v2 f squared. Now, after the collision, the golf ball is moving at 1.94 meters per second. The club, after the collision, is moving at 0.760 meters per second. What do we get the final kinetic energy of the golf ball and the golf club to be there? Yeah. For initial? What'd you get? 0.1422? Okay. 0.142 joules, thank you. And what do we get the final kinetic energy to be? My guess is it's going to be less than 0.142. Hey, what if it works out to be more than 0.142? What happens? We made a mistake. It's not going to be more. It's either going to be the same or it's going to be less. I think it's going to be less. But we know it's not going to be more. Jack, what is it? 0.1398? Okay, so 0.140. That's actually quite a bit closer than I thought it would be. Okay, I thought it was going to be quite a bit lower than what we started with. But it's still enough lower that we would still consider it to be what kind of collision? Inelastic, right. Now, question number 2. There's probably people that did question number 2 without even doing a calculation. If you have an argon atom striking another argon atom, both with the same masses, and one of them is moving at 17 meters per second before the collision, one of them is moving at 20, and after the collision, one of them is moving at 17 and one of them is moving at 20, then we know just by looking at those numbers that the kinetic energy initial will equal the kinetic energy final, right? 1/2 of 6.63 times 17 squared plus 1/2 of 6.63 times 20 squared is equal to 1/2 of 6.63 times 20 squared plus 1/2 of 6.63 times 17 squared, right? Does that make sense? So if those two numbers are equal, what kind of collision is it? What? Pardon me? It's elastic collision, right? And we know that because the kinetic energies are the same. It's not a big surprise there, right? Okay, that would probably be our prediction for this question. We're talking about argon atoms. We're not talking about subatomic things, but we're talking about real close to subatomic things, right? Yep.
solid object, I decided that we see like if you have a ball of like steel or something.
Yep.
And you hit it with a swifted bullets, would that be elastic on that large scale?
Good question. If you have, Rucker says, if you have a really, really solid object, piece of steel or whatever, and you hit it with something that's also really, really solid, really, really hard, at that scale, would it be considered to be elastic? Possibly to 3 digits. Okay. At some point, it will be, Rucker, inelastic. At some point, there will be some compression, and therefore there's going to be some kinetic energy lost. But to 3 significant digits, it might be the same number, which would mean that it would be elastic. So don't assume that because it's not subatomic, you're not going to get any elastic collision. In all likelihood, you will, okay, but not for sure. That's why you've got to crunch your numbers, unless the two objects stick together, right?